Today we are doing a deep dive on CoTracker3, which is a state-of-the-art point tracker. It beats other point trackers out there. And what's fascinating about this paper is that there's a lot of interesting concepts and techniques built into the architecture, and there's a lot to learn here. So the purpose of any point tracking algorithm is to understand the movement in details and precise way of any point you want to track. So usually it would take a video as the input, and then you would specify points here that you want to track, for example, on this person. And the whole point is that the model is supposed to keep track of those points throughout the video and build the trajectory of that point as it navigates in time and in space throughout the video. But that's not the interesting thing. The interesting thing is that there's going to be a lot of challenges. So the object can be far or near, it can move fast or slow, and it can be occluded. So it can be occluded behind an object here, it can be occluded behind a person. It can even go outside of the frame of view where you might not see it. And the challenge is to track the point throughout the video despite all of these challenges. So how does CoTracker3 look like in a live demo? So we're going to take a video and we're going to manually annotate points on the person, and then we want to track those points. And of course, in other words, we're going to track the person and the bicycle as it moves in the scene. The model is going to predict the trajectory of those points. I want you to imagine that every one of these points are actually tokens or embedding vectors. Each of the embedding vectors, they're going to be like experts, and they're going to contain a lot of information within its encoding. So it's going to contain information about the appearance of the area where the point is. Okay, so the patch is going to contain the motion, past trajectory of where the point was in the past. Is going to contain information about whether it's visible or not. Is it hiding behind something? Is it being occluded? Is it part of the background, or is it part of something that is being moved, for example? It's going to understand, am I seen? Am I being occluded right now? What is my relationship with neighboring points? Is the point next to me part of the same object that I'm trying to represent, or is it another object, for example? So as we start playing here, you can see that for every frame, there's a kind of an update going on. So these tokens for every one of these points are being constantly updated with new signals, new information that constantly update their view on the appearance, the motion, the visibility, the occlusion, the relation with other points. And the trajectory that rainbowy effect that are left behind the cyclist here shows that those embedding vectors contain the necessary information needed in order to track really well. In this part, the cyclist went outside of the frame, so we no longer see it, but those embedding vectors have that information that it has left the scene, but it's still there in real life. It's just not in the frame, and that knowledge is still encoded in those embeddings. At this point, we go behind a person, so there's an occlusion, and those embedding vectors, it shows that they understand that due to the motion, the object, the cyclist, is still in motion. It's no longer visible, and there's something else that is between it and the view. And finally, it emerges, and those points are still tracked despite the occlusions. As we processed the video frame by frame and collected new information, we updated those embedding vectors in the right way and in such a way that it understood the complex motion going on. It understood the occlusions. It understood the appearance that there's a bunch of points that are tracking the same thing that are different than the background. And we're going to see how the architecture of the model is put in place to allow those embedding vectors to be learned to produce such great results. So some cool features we're going to see all of those points and tokens I've spoken about, and I've shown how they communicate with each other in space and in time. There's going to be a correlation with all of those. And so we're going to talk about 4D correlation. We're going to talk about how there's a sliding window. It's impossible to process a 2-minute long video in one shot. It's not going to fit in the memory. So we are limited in whatever we can, the amount of information we can process. However, we can choose like a smaller fixed window size, let's say a few second long video, and process the information there and somehow propagate that information. We slide the window further in time, and then we propagate the information we processed earlier to that new window. We call that technique sliding window. We're going to talk more about that. There's also the concept of virtual tracks, or these proxy tokens or helper tokens to assist the tokens that track. We assist them with the other information that can help in terms of occlusions or going outside of the frame or understanding the context. So there could be other expert tokens out there to assist the actual tokens, which are the points themselves. We're going to talk about multi-scale feature-rich representation. So the tracking relies on the features, which are the output of some kind of a CNN encoder of the image. And the richer those representations are, the better the track is going to be. So we're going to talk about how they're going to make those representations super rich. There's also, for example, the transformer. Usually a transformer is trained to predict the next token in the sequence, but in this case, they're actually producing iterative updates to certain pieces of information incrementally. So that's like a neat feature. The other thing, all of these points are actually tracked jointly, so the whole thing is processed all together. So all of these new features can be found in the paper, and we're going to learn about that. So traditionally, the two main camps of research was either long-term sparse point tracking. So the idea here is because of the limited amount of memory or compute we can have, we're either picking just a few sparse points, or like they can be edges or corners or whatever, and the focus is to track them robustly through many long sequences, right? This could be good for structure from motion, which is, you can move on to 3D reconstruction. It could also be good for simultaneous localization and mapping. The other side, instead of tracking something for really long, you can actually track many points densely for short term. And this is more in the camp of the optical flow, where the idea is you want to estimate motion vectors of all the pixels in the scene. Usually that's done for motion segmentation, or if you want to interpolate between video frames. There are some challenges there. If the illumination changes, or if there's super large displacement in the object, those can be drawbacks to methods like that. So usually it's a spectrum between those two camps. Now, where CoTracker lies is actually bridging the gap between those two. So CoTracker, it actually tries to track densely for long term. And this is the third version of CoTracker. So compared to its predecessors and also other algorithms, CoTracker3, it's simpler, it's better, obviously. It has a very nice architecture that's more efficient. And they also say it's learned using pseudo labeling on real videos. So what they mean here is that, as they say here, most state-of-the-art point trackers are trained on synthetic data. The reason is because it's very difficult to annotate real videos here. And so they can't just rely on synthetic, they need the real, but there is a statistical gap between the synthetic and the real. So one thing that they do is that they're going to generate pseudo labels using off-the-shelf teachers. What they mean is that they're going to get other point trackers to do the labeling, okay, for them and generate sort of free annotations on real videos. Now, given that they're not perfect, they're not ground truth data, there's going to be some noise to that. There's going to be some imperfections in those predictions. However, when you have many teachers doing the same thing, actually the noise gets reduced, and so those predictions become more reliable. By doing that, it's a form of knowledge. It's a form of knowledge. Okay. Anyway, it's a form of knowledge distillation, where the CoTracker is like the student, and the others are like the teachers. And as they say here, the student benefits from learning from a much larger noisy data set. And as there's many of those teachers, there's going to be kind of an ensembling effect, and that's going to reduce the pseudo annotation noise. The student model is going to inherit the strength of different teachers. So this is what they mean here by pseudo labeling on real videos. And one more thing is that having all of these teachers provide all of this quote unquote free annotated predictions gives a kind of a head start to the training and learning. So the training becomes more powerful as there's a strong prior before the training. So we're going to start with the architecture, which is right here. And I personally found the architecture a bit too simplistic, not explaining too much. But looking through the code, we're going to understand it a bit better. So the first thing is that you're going to have a video, okay, and you're going to have these query points, okay. Before any tracking takes place, we're going to need to encode every frame into an embedding. And the richer the embedding, the better the tracking. So let's see how they encode every frame here. Okay. So this is your sequence of frames. The frames, they go through a convolution layer where every frame passed through the conv produces a 64 dimension feature map. Okay, so we're going to have 64 feature maps. And as it says here, there's a section on feature maps that they're going to compute a d-dimensional feature maps with a CNN for each video frame. They're going to downsample the input by a factor of 4. And then they're going to compute the feature maps at 4 different scales. So they're going to downsample it by a factor of 4, and then they're going to compute feature maps at 4 different scales. There's the pyramid of features here. And they're also going to downsample by 4 to create richer representation. We're going to see how this is done. So as mentioned, they're creating a 64 channel of feature maps. They are going to downsample it 4 times. So they're downsampling it once, downsampling it twice, a 3rd time, and 4th time. The reason for this is that at this point here, that's the highest resolution. When you have high resolution, then you're able to capture fine details. You're able to understand the exact location of an object, for example. As you're downsampling, you're changing the resolution. You're changing the scope. Now, some of the object can be small, and it's easier seen here. Some of the objects are big, so you actually need to downsample to actually locate it better. Some of the object can move slowly, some of the object move fast. If it moves fast, it's better tracked at this level here. You can also understand the context in a more broader sense here of what's going on in general. So this hierarchy of features right here allows the model to see, to locate and track objects that are small or big or slow or fast, or just understanding the context at a fine level or at a coarse level. And for each one of those, we're actually going to concatenate them and create this super rich long vector. Now, because they are at different resolution and sizes, we need to upsample them. We're going to upsample them using bilinear interpolation. So now they will maintain their richness, but they will have the same size. We're going to concatenate them along the channel dimensions. Doing that allows us to combine all of this information from those different levels. Right here, we're going to end up with like 450 depth-wise in terms of the channels. By doing a convolution, we're going to end up around 256 channel, and then we'll pass it through a one-by-one convolution. And the point there is to preserve the spatial dimension of those feature maps, but reduce the number of channels a bit so that you end up at 128, because we might not need that many channels. We do want it to be compact. The more this tensor is compact, the more you can also focus on the tracking. So you want to have a tensor here that is able to capture as rich information as possible while keeping it compact, because there's another stage. And so once again, this representation, it combines information from different scales and allows to understand, or allows the model to learn complex relationships between all of the different channels. We're going to do this for every frame. So that's the downsampling part. For the feature pyramid is that we're going to take the output and then we're going to scale it down by half to produce this one, and we're going to do this again to scale it down by half, and then we're going to do this one again and scale it down by half. This is going to create our feature pyramid here to have the same kind of richness but a different resolution. And this pre-processing is going to allow the tracking to process information at various scales more robustly. And so these two right here, that's the final that's the process to produce the feature maps that are talked about in this section, which is this module right here. So once we have our feature maps here for every frame, we're going to compare it to something. That something, it's an embedding vector that represents the track here. How are we going to create that embedding vector? Well, we're going to take our track right here, and let's say we slice a frame, which is represented by this one. We're going to take we do have the ground truth of the location of that point at a certain time. We're going to create a kind of a support grid around it, just sampling many points just nearby. That allows to actually understand the context. So instead of tracking just the point, we're going to track this patch right here. It's going to make it more robust. It's going to provide a local context to the point. And we're going to take that and we're going to go to each one of these levels in the pyramid, and we're going to extract that patch in the feature pyramid corresponding to this grid right here. So we are extracting the feature maps for those specific points, and we're going to do this for every slice right here, and not only for every frame, but we're also going to do it for every level of the pyramid. We're going to have 4 levels of embedding vectors representing the track embedding vector. So we're going to talk about the 4D correlation features here. So what they're trying to correlate or compare is actually each feature vector around the query point of the feature map, whatever was encoded by the CNN, to each feature vector around the track point of the tracking feature. So basically here, it's as if we're taking a crop of the object we're trying to track, and we're comparing it at every spatial location here and here, and we are doing that for the other frames as well. You know, and so what we're trying to do is that we're trying to see, is this does this crop here, does it how well does it match this part of the image in the feature map space, and how well does it map at this location, and how well does it map at this location, this other frame. And for every comparison operation, we're going to get a score. Okay, and so we're going to collect all of these scores at different scales. So there's, as we mentioned, there's four scales right here. And so for every scale, we're going to do all of these comparisons, and we're going to end up, all of these comparisons will be put in a correlation volume. So for each one of these scale, you can think of correlation volumes as heat map. That's where the point that matches the most, the appearance of the object with the part of the feature map, is going to be the hottest. And so this is how CoTracker actually, this is the operation, the main operation that helps the model locate the object within the frame and then track it over time. Now, because you have all of these correlations at different scales, we actually want to boil it down to one. So we're going to pass it through an MLP and downsize it. We're going to compress that and combine all of this multi-scale information, and we're going to learn a more compact representation of the correlation. And that leads to the next part, which is, that's one part of what's going to go into the transformer. So that's this part. We also have the embedding of the tracks themselves. We have embedding of the visibility, which is a separate input. We also have another input right here that I didn't put, but it's the confidence. And one more is the flow embedding. So this comes from more the optical flow research, where we're gonna subtract the coordinates between one frame and the previous one. And that subtraction, that diff between those two coordinates, is gonna give us the relative motion between this and that. Once we have the relative motion, we pass it through a positional embedding. So we're gonna get embeddings for those motion vectors. And we are gonna have our flow embedding right here. And so this is the input that's going to be fed to the transformer. For all of this to be fed into the transformer, they need to be tokenized. So they're going to be transformed into tokens, and it's going to be one big sequence of token. And then the transformer is going to process this input. It's going to go through multiple layers of attention, and it's going to iteratively refine its prediction. Now, the transformer is not your typical transformer. They have their own transformer right here. So this input right here gets transformed to this 1D sequence of tokens, and they have a chain of different attention and cross attention module in their own transformer. The first one is a temporal attention. So they're gonna focus on the time, how all of these, they're gonna sort of know which one comes first based on all of this information. And the output of that is gonna be, they're gonna be tokens that are expert in time. So they're gonna be, their awareness of time with respect to each other is gonna be enhanced by going here. In other terms, given the history of the trajectory of the point, they're going to try to predict the future trajectory given the motion and the appearance and the correlation volume, the correlation between the features. Once they have these new tokens or time tokens, they're going to split them into two. Most of them are going to be the tokens that are going to be responsible for tracking the points themselves. Okay, so these are the actual tokens that have information about the query points, the points that we're trying to track. There will be other tokens, which they're virtual tokens or helper tokens. They're going to focus on the broader context. For example, if the motion of the camera is trying to change, or if there's any changes in lighting conditions, or the relationship between the objects, all of these information need to be encoded somewhere. and we're going to encode them in these tokens right here. Okay, and so there's going to be a kind of interaction, intermingling between those two sets of tokens. The end result will be richer in tracking. Okay, the next thing we do is that the virtual tokens are going to attend to the actual point tokens. There's going to be cross attention. So another way to think about that is, let's say we take, for example, the motion of the camera. So, you know, how is the motion of the camera attending to each one of the point, or how is, for example, point 1 important to the camera motion? How is point 2 important to camera motion? This is just like an example. After going through the cross attention right here, it's going to go through a self attention, and it's going to attend to itself. It's going to exchange information with itself. The layer after that, it's a cross attention, but this time it's from the point token's perspective. And so point 1 is going to say, okay, how much the camera, how much should I, focus on the camera motion, or how much should I focus on the lighting? How much should I focus on the person I'm being occluded by, for example? And so here you can think of it that the point trackers are improving their own representation based on the context of the video. The output of that goes through a linear layer. And so here the tokens are going to update themselves. At this point, there is no exchange of information. They just update themselves based on all of this information. And the output of the linear layer is going to be a tensor. And at the end, it's going to have a dimension of 4. So the first 2 dimensions will actually be a delta of the coordinates, going to be little incremental improvements for the points that are being tracked. There's also an incremental for the visibility, incremental of the confidence. How did we end up with a delta? It is because of the losses that we actually use. And so for the coordinates, we use Huber loss. It's a kind of a combination between the L1 and L2 loss based on like a threshold, and where they compare the tracks with the predicted track. Because it's an L1 and L2, by definition, that's like a delta. And then they're going to use the binary cross entropy for the visibility, and then the confidence. And then there's another operation to extract the delta from there. So the output of this transformer are updates that are going to happen. These updates, they're added back to the input, which is this part here of the input, and that ends the first cycle of a pass through the transformer. Once you have that information, once you have new track features, then you are going to perform the correlation once again. Because you have updated track features, you're going to end up with a new correlation volume, and that new correlation volume is going to end up here to update the input. As you have a new input right here, then the second cycle of the transformer starts, and the output of the transformer once again will be those deltas, which are going to be added to the input, and then so on and so forth. We're going to repeat that a few cycles, and that's how the model is trained. And by incrementally adding one delta after the other, the tracks are going to learn to, the predicted tracks are going to learn to match the ground truth tracks. And that's how the model is trained to actually use the features of the video and those initial query points, and then predict the trajectory of those points that passes through all of these sequence of frames that go behind the sand dune right here, go behind the person, and still being able to be tracked right here.